Welcome to Study Loop.
For part A, we want to consider a particle in a box whose wave function is given by the normalized wave function psi, which is equal to a times e to the minus alpha times x squared plus y squared plus z squared, where x, y, and z are the dimensions of the box, and a and alpha are real and positive constant values. So the value x squared plus y squared plus z squared can be written in spherical coordinates as r squared. So r squared is x squared plus y squared plus z squared. So I just replace that with r squared in our expression for the wave function psi. The probability of finding a particle between r and dr, which is what we're asked to find, p is equal to psi squared times the dv, where dv is the infinitesimal change in the volume of the sphere. So we can replace psi with our function for psi, which is a e to the minus alpha r squared. So we replace psi with that and square it. So this is a squared times e to the minus 2 alpha r squared. And then dv, since it's spherical, is 4 pi r squared dr. And this is actually our expression. So a was pretty simple, and we can box it in as the solution to our expression. Now, for part B, to determine what value of r causes the probability to be maximum, we want to recall that a function maximum when derivative with respect to that function is equal to 0. So when dp dr derivative of the probability with respect to r equal to 0, we're at a maximum value, so long as the square is also equal to 0, because it's going to be. So how do we make sure assume is a maximum? Well, we want to measure also d squared of p. Excuse me. There are requirements for this to be a maximum of a function. So let's do the first one, dp dr. So remember that the probability function is written above, so that's the probability function we're going to be taking the derivative with respect to. So dr So first we have the 4 pi r squared. So 4 pi r squared, we can just pull the 4 pi because that's not a function of r. We'll have a squared function of r. We can pull that out. We have 4 pi a squared d by r of r squared e minus 2 alpha r. Okay, so we are going to use the chain rule here. So this is equal, again, pi alpha squared. Let's take the derivative with respect to r squared. So this is 2r, and then e to the minus 2 alpha r squared is done. Next, we can take the derivative with respect to what's in the exponential, and the r squared alone we're going to add to this is plus r squared times minus 4. So the derivative of what's in the exponential, multi-exponential, e to the minus 2 alpha r. Okay, so setting this equal to 0 and simplifying, we have a squared times r times e to the minus 2 alpha r squared minus 2 alpha r to the third e to the minus alpha r squared. This is all 0. So we can divide by 8 pi a squared, and that'll cancel out. And then we can also pull out the e to the minus 2 alpha r squared, so that's also going to cancel out. And what we're left with is r is equal to alpha r to the third. Or in other words, r is equal to 1 to alpha, the square root of alpha. The positive goes, we add that to the other side, or the negative goes away. 1 over 2. So therefore, the two extremes, of course, are r equals 0 and r equals 1 over 2 alpha. So when r equals 0, p equals 0. That's a minimum. Therefore, to determine if r equals 1 over 2 alpha is indeed maximum of p, we have to take the second derivative of p. So now let's go ahead and take the second derivative of p. Ability. Instance, this is 8 pi times a squared. Again, we take the derivative with respect to r of what is inside. So we're taking derivative with respect to r of, let's box it in green here, of this. So we have e to the minus 2 r squared. This 4 r times e to the 2 alpha r minus 2 alpha multiplied by 3r squared minus 2 alpha r squared minus, we ran out of room here, so let's write it below, 4 alpha r to the 4 e to the minus 2 alpha. Okay, so now we can even further simplify this. First of all, we can pull out the e to the minus 2 alpha r squared, because that's common in all of them. And then further simplifying, we have this being 2 a times alpha r on that front. And then this is multiplied by minus 10 alpha squared plus alpha r to the 4th. Okay, so now we can replace r with the value 1 over the square root of 1 over 2 alpha. And so, of course, that value is squared. So what this becomes is, so this is just replacing r with the square root of 1 over 2 alpha. So we have 8 pi. So you have e minus 2 alpha times 1 over 2 alpha. So this is e to the minus 1. Again, that's replacing r with the square root of 1 over 2 alpha. So that gets squared, so that becomes 1 over 2 alpha. Cancels with that 2 alpha, so it's just negative 1. By 1 minus alpha times 1 over 2 alpha plus 8 alpha times 4. Okay, and simplifying even further, becomes, we have 8 pi times 8 e to the 1. And then everything in the parentheses becomes negative 2. Oh, this alpha squared. That alpha squared. And that alpha, missed that previously. So now we want to make a comment about this. So notice that the constants 8 pi, a squared, and e to the minus 1 are positive. And so the negative 2 factor causes this to be less than 0. So this is indeed less than 0. This is because a squared is positive. So therefore, this is less than, not less than 0. So therefore, the maximum of the probability is at r is equal to, so we can say max, just confirms it by that check there. R is equal to the square root of 1 over 2 alpha. So in problem 41.42, where the wave function was psi equals to a x e to the minus alpha x squared b to e to the minus beta y squared e to the minus gamma z squared, a maximum of the probability distribution function occurred at x equals plus or minus 1 over 2 alpha. However, a minimum of both the wave function and therefore the probability occurred at x equals 0. Here, there would actually be a maximum of psi equals a to the minus alpha r squared at r equals 0, because psi of 0 does not equal 0. You can go ahead and try it. Plug in r equals 0. E to the minus 0 is 1, so it's not equal 0. However, since the probability this time includes a power of the variable r, unlike in the rectangular coordinates, the probability also turns out to be 0.